Hello. So this is part 3 of our Kinetics video series. Kinetics is one of the first things that you study in your Chemistry 2 semester, and so I put these series together on kinetics and rate reactions so you can easily understand and work the problems. So for a review, determining the order of reaction, if you have, say, molecule A, and you want to turn that into products, we want to time how long it takes for the reaction to start. So time the reaction. So the rate, of course, is how the concentration of A, and A is I'm just using this for a generic molecule. The rate is how the concentration of A gets used up over a period of time. So the rate depends on the concentration of the reactant, usually in orders of a reaction. Now remember, the order of the reaction, that doesn't mean a chronological order. This is a numeric label of what category these reactions fall into. It describes how fast the reaction happens. So we have 0 order, 1st order, and 2nd order, and these are just the reaction depending on how fast it is. Now this can only be determined experimentally with your reactants. And remember, the reactants are what is on the left-hand side of the yield arrow. The reactants are like the ingredients. If you're making a recipe, if you're cooking in the kitchen and you're making a cake, the flour, the sugar, and the eggs, those would all be the reactants, the ingredients. And then the products would be the cake itself, what you end up making with all the ingredients. So we're talking about the reactants, the molecules on the left-hand side of the arrow, of the yield arrow in a chemical formula. And these can only be determined experimentally, and the experiment is called the method of initial rates. And initial rates is the time it takes for the reaction to start happening. So the initial rates at the beginning of a reaction, they're measured at different concentrations of the reactants, and you do one experiment at a time, and in each experiment you change the concentration of the reactant, and you time how long it takes for the reaction to start happening with the different concentrations. Now, if you remember the reaction order, again, order doesn't mean chronologically. Order is a label saying how the rate is dependent upon the concentration of the reactant. So 0 order, the rate is independent from the concentration. The rate does not change no matter how much you change the concentration. The amount of time it takes for the reaction to happen stays the same, no matter if you have 10 moles of A or 10,000 moles of A. It's not going to change the rate. So you can see down here in this little experiment box, we have experiment 1, 2, and 3. And here's the concentration of A in molarity. So we have 0.10, and at 0.10, it took 0.015 seconds for the reaction to start happening. But then we double that concentration from 0.10 to 0.20, but the initial rate, how long it takes for the reaction to start happening, stays the same at 0.015. And then we double this again from experiment 2 to experiment 3. We go 0.20 to 0.40. That's doubling it, but the initial rate stays the same. So if the rate stays the same no matter how much you increase the concentration, this is called zero order because the initial rate has zero change. And it's written like this. You put the brackets to designate concentration, and then you put the molecule in there. We're just going to use A. And then you put a little zero up as an exponent for zero order. Now let's look at first order. And these are gone into much more detail in the first two videos. So if this is confusing to you, go back and review the first two videos. Actually, the very first video is the one that goes into detail about finding the order, but this is just a review. So in the first order, the rate is proportional to the concentration of the reactant. So here's the concentration of the reactant. This column, the concentration of A. We start out with 0.10 again, and the initial rate is 0.015. But then in experiment 2, if we've doubled the concentration, we've gone from 0.10 to 0.20, look at this. The initial rate has also doubled from 0.015 to 0.030. So we doubled this concentration, and the result was the reaction rate also doubled. Now let's look from experiment 2 to experiment 3. We doubled the concentration again from 0.20 to 0.40. So that's times 2. We doubled it. And look over here at the rate from experiment 2 to experiment 3. The rate goes from 0.030 to 0.060. So that doubled as well. So since we have two under the concentration, for the concentration of A, every time we double the concentration, and we have the initial rate right here, the initial rate doubles. So to make this equation correct, 2 equals 2, we need an exponent up here, and that exponent is 1 because 2 to the first power equals 2. So this 1 means it's going to be the first order. So as you can see, the rate is proportional to the concentration. As the concentration is doubled, the initial rate also doubles. Now second order is similar to the first order. The rate is also proportional to the concentration. As you increase the concentration, the rate increases. But instead of increasing the same, like in the first order, when you doubled the concentration, the rate doubled. In second order, it's proportional to the square of the concentration. So when you double the concentration, then you square that concentration, and the initial rate is going to quadruple. And let's look at this chart to see how this plays out. In the first experiment, we have a concentration of 0.10, and the initial rate is 0.015. Well, we double the concentration, and we go from 0.10 to 0.20, so that's times 2. But look at the initial rate. We start out with 0.015, and as we double the concentration, this initial rate gets quadrupled from 0.015 to 0.060. So that gets quadrupled. And then let's look at experiment 2 to 3. The concentration is once again doubled from 0.20 to 0.40. This initial rate is also quadrupled from 0.060 to 0.240. So that is quadrupled. So the concentration is doubled, and as a result, the initial rate is quadrupled. So in order to make that equation make sense, we put an exponent in here. The exponent would be 2 because 2 to the second power is 4. So that 2 makes it second order. Now, that's all fine and good for when we're doing a simple chemistry formula like A yields products. But that's not what we're really going to see in real life and in class, right? We're not going to take hydrogen and just make products out of hydrogen. We're going to take hydrogen and something else. Or we're going to take carbon and oxygen and make something with it. So we're not just going to have one reactant. We're going to have more than one reactant. So let's say we have reactant A plus reactant B, and that yields products. This is more realistic. So we could have, this could be like carbon, and this could be oxygen, and the product could be CO2, something like that. But we're just using generic A and B for the reactants right now to make this simple. So how do we determine the orders for the reactants when there's more than one reactant? So here we are again, we have A plus B equals products, so that's multiple reactants. The reactants would be the A and the B, because those are on the left-hand side of the yield arrow. And we do this by our good old method of initial rates experiments, just like what we did with those charts a second ago. But what we do, it's the same for a single reactant experiment, but what happens is one of the reactants' concentration is held constant. It stays the same. And then the other reactant's concentration is the variable. So we only change the concentration of one reactant at a time in different experiments, and then we compare them. So here's an example. So as you can see, we have A plus B equals products. So the reactants here are A and B. So down here on the chart, we have the concentration of A in this column. We have the concentration of B in this column. And here's the initial rates that we timed. Now, if you look at the concentration of A in the first column, you can see that we have 0.10, 0.10, 0.20, and 0.40. Now, look at this with the 0.10 and 0.10, these are the same. See, we held the concentration of A the same at 0.10 both times. So this is going to be constant. So we're going to use this as the control for the experiment of these two concentrations of reactant B. Because if you notice, B is what the concentration of B is what we're changing here in these two experiments. Here's experiment 1, experiment 2, experiment 3, experiment 4. So the first two experiments, what we change up is the concentration of B. And as we go from 1.2 molarity of B, and then the next experiment, we do it at 2.4 molarity, that means we've doubled the concentration between these two experiments. And let's look at the rate, the initial rate over here. This initial rate stayed the same. So that's no change. Or another way to put no change is 0. So the concentration of B would be a 0 order, and so you put the 0 up there as an exponent after the concentration of B. Now let's look at the rest of this chart. if you look at the rest of this chart, if you look over here in the very left in column A, this is the concentration of A. On experiment 3 and experiment 4, we changed up the values of the concentration of A. In experiment 3, the concentration of A is 0.20, and then between 3 and 4, we changed it up to 0.40. So we doubled that. Now let's look over here in column B, the concentration of B. See how we kept B the same at 3.0 molarity? So we kept B at a constant. We kept the concentration of B at a constant. So that way we can use the concentration of A as the variables in these last two experiments in 3 and 4. So as we already said, between 3 and 4 we doubled the concentration of A from 0.20 to 0.40. So now we need to go over and check and see what it did to the initial rate. And look, it didn't change anything. The initial rate, the time it took for the reactant to happen, is still just 0.015. So this is also no change. So that means it's 0 order for A as well. So we're going to write that with the little brackets denoting concentration, A, and a little 0 up there is the exponent for 0. Here is the concentration of A in this column. Here is the concentration of B in this column. And here is the initial rate time in this column. And this is in seconds, by the way. So let's look at A first. In A, the first two experiments, we have experiment 1, experiment 2, experiment 3, and experiment 4. So in A, these first two experiments, we did not change the concentration of A. We left those as a constant. Or we could also call them the control group. So we can, since we left these first two experiments, the concentration of A, we left them the same, unchanged. We can use these two experiments to look at the B column, the concentration of B. And between experiment 1 and experiment 2, we have doubled the concentration of B from 1.2 molarity to 2.4 molarity. So that's doubling it. So we doubled the concentration of B. So now let's go over and look and see what it did to the rate. And it did not change. The rate stayed the same even though we doubled the concentration of B in the experiment. So no change. That means 0 order for B. And this is for B because B was the variable. B was the ones we changed the concentrations up in. So we're going to write B with brackets and a little 0 next to it. Okay, let's go back to the experiment 3 and 4 now. Over here in column A, experiment 3 and 4, we doubled the concentration from 0.20, and we measured that, and then we did another experiment and we changed the concentration to 0.40, and we measured that, and this is the concentration of A. And meanwhile, in the same experiment, we have B here, but we left B alone. We just left B at 3.0, the concentration of B at 3.0 molarity. So we left these alone, so this can be the control, so we can just not worry about B and pay attention to what A is doing over here. So, as we said, we doubled the concentration of A over here between experiments 3 and 4. So now let's look at how it affected the initial rate. So the initial rate was 0.030 when the concentration of A was 0.20. And then in experiment 4, when we doubled the concentration of A, this rate went from 0.30 to 0.60. So this rate also doubled. So as we doubled the concentration of A from 0.20 to 0.40, we doubled the rate from 0.030 to 0.060 seconds. So since the concentration of A was doubled and the initial rate time was doubled, then what would we put up here as an exponent to make this equation true? That would be a 1, because 2 to the first power is just 2. So this is going to be first order. But we have the concentration of A and the concentration of B in this chemical reaction. Remember, A plus B yields some products, and that's what we're testing. So what we do is we look at the concentration of A, the one that doubled, and that's what's going to be first order. So the concentration of A is going to get this little 1 exponent next to it to show that it's first order. So B got a 0 exponent because when we were changing the concentrations of B, the initial rate remained the same. But as we doubled the concentration of A, the initial rate also doubled. So this is going to be first order, and getting A is going to be in first order and getting a 1 as an exponent. Okay, so one more time for practice. We have experiment 1, experiment 2, experiment 3, and experiment 4. So first, let's look at the concentration of A. The experiment 1 and experiment 2, we both have 0.1 molarity of A. The concentration stayed the same. So this is our control. So we're not going to look at this. We're going to look at the concentration of B in these two experiments. And when we went from experiment 1 to experiment 2, we went from 1.2 to 2.4. So that means we doubled the concentration of B in this experiment. Now let's look over here and see what it did to the rate. And the rate went from, as we doubled the concentration of B, the rate went from 0.015 to 0.060. Now that's not doubling, that's quadrupling. This shot up 4 times. As we increased the concentration of B 2 times, the rate was increased 4 times. So let's write that down. As we doubled the concentration of B, the rate, the initial rate, quadrupled. It went up 4 times. So what do we need as an exponent next to this 2 to make this equation correct? We need a 2, because 2 squared equals 4. Since we put a 2 as an exponent there, that means it's going to be second order. Now, which reactant is second order? Well, it's going to be the concentration of B is going to be second order, because that is the one where we were messing around with different concentrations to see what would happen. So B would be put the concentration of B, so B in these brackets, and we would put a 2 up here as an exponent. Now let's look at experiments 3 and 4. So if you look at column B, experiments 3 and 4, we left these the same. We left them at 3 molarity. So this is the control for the concentration of B. So we don't have to worry about these. We're just going to look over here at the concentration of A in experiment 3 and 4. So we started out with 0.20, and then in experiment 4 we doubled that to 0.40. So we doubled this to 0.40. Now let's look over and see what that doubling did to the initial rate. So the initial rate was at 0.100, and as we increased the concentration of A from 0.20 to 0.40, the initial rate increased from 0.1 to 0.2. So that also doubled. So if we write this down, the concentration of A doubled, and the initial rate doubled. So what do we need as an exponent up here next to this 2 to make this equation true? We need a 1, because 2 to the first power equals 2. So that means that A is first order. And we write this with A in the concentration brackets and a little 1 after it. Now, what do we do when once we find this? Once we find the orders out for each of these individual reactants. And you notice I'm not finding out the orders together. You have to separate each individual reactant and do it each individually. So let's say we found out that the concentration of A was in the first order and the concentration of B was in the second order. So what do we do with that information? Well, we need to add these orders together. We need to add the orders together to find out the overall order of the entire reaction. So 1 plus 2 is 3. So this would be a third order reaction. Overall, the entire A plus B equals products would be a third order. Now remember the rate law. Before we had rate equals that rate constant, that K, times the concentration of A to whatever order number it is in that exponent. But now that we're dealing with more than one reactant, we're not just dealing with A, we're dealing with B too. So the rate law, you just multiply the other reactant and its order exponent onto the formula. So we have the rate equals, the rate constant is the K, and that just stays there, times the concentration of A to the M, and M is just going to be the order number. So say if A was in the first order, and then times the concentration of B raised to the power of B's order numbers. So let's say B had a 0 order. I'm just making these up. So we would have rate equals K A 1 B 0. So we would take that 1 and that 0 and add them together, and we'll get 1. So this would be overall first order reaction. So you just add them up is all I'm saying. You just add up the orders of reaction, but you have to figure out each individual order of reaction for each individual reactant first, and then you add them up.